Good morning, everyone. My name is Sachin Khandelwal from batch CSE, section A3B3, roll number 56. Today, I am going to talk about a very important topic is quantum computing, discharge algorithm. In this presentation, we will we will start from the limit of classical computer, then see how quantum ideas like superposition give us give us more power. After that, I will explain detached problem, how a classical computer solve it, and then how detached quantum a classical computer solve it, and then how detached quantum algorithm solve it with only one query. Finally, we will see why a small example is actual a big milestone for the future of quantum computing. So let's begin a journey into a detached algorithm, a quantum leap. So now let us discover why detached algorithm is called a quantum leap. Detached algorithm solves a small but very important problem. We argue a black box function that take one bit as input and gives one bit as output. Our task is only to decide whether this function is constant or balanced. Detached algorithm does something much smarter. This this speed up is small, but it was the first solid proof that quantum computer is powerful and useful in future for all industry and people. That is why we call it quantum leap in the history of computing. Means and they have many powerful things. Embark on a journey into the fascinating realm of quantum computing, uh, beginning with a beginning with a, foundational breakthrough showcase the key benefit of quantum computing, exponential power with fewer operations. Then upon the world before classical uh, communication competition limits, before quantum advancement, our understanding of communications or was confined to classical model facing inherent limitation. The world before we talk about detached algorithm and quantum advantages, let us look the world before classical communication. The classical computers use bytes, which can only be 0 or 1 to solve inputs step by step. For small problem, this work very well. But when the problem becomes very large with many problems inputs, a classical computer quickly hits its limit. For example, if we have if we have a function and we want to know how it behaves on many inputs, a classical computer has to check each input but but a classical computer have to check each input separately. The number of steps can grow exponentially. Classical computer also struggle to simulate quantum system, the like atoms and molecules, because their behavior is naturally quantum, not classical. In simple words, classical computers are powerful for everyday tasks, but they become too slow or even impractically for very complex problem. With huge search space, these limits are the main reason scientists started to look for a new model of computing, which lead to quantum computing, and as an early example detached algorithm. Then 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 now I will introduce one of the most important ideas of quantum computing, introducing quantum superposition more than zeros and ones. There is no in between, but in quantum computing, a qubit can be in a state that is combinations of and 0 and 1 at the same time. We call this superposition. You can think of it like a coin. A classical bit is like a coin that is already lying on the table as heads or tails. A qubit in superposition is more like a spinning coin in the air. It is not just head or just tail air. It is in a mix of both possibility until we catch it. And 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 look and look when we measure a qubit, the superposition collapse and we see either 0 or 1 with certain probabilities. This is the idea is very powerful because a qubit can be in superposition of zeros and one. A quantum computer can, in some sense, process many possibility at the same time. This is the key that allows algorithm like Deutsch algorithm to get information about multiple inputs, which only one quantum query, instead of checking them one by one like a classical computer. At the heart of quantum computing lies superposition, allowing qubit to exist in multiple states simultaneously. Unlike classical bit, qubit is equal to a coin. I am saying before. Classical bits means either 0 or 1 at any given time. Quantum qubit means can be 0, 1 or both simultaneously. Then now let's look at Dita's problem. A yet yet profound challenge. A simple yet profound challenge. The problem itself look very small and simple. We are given a black box function f that takes one bit as input and gives one bit as output. So the input can only be 0 or 1 and the output is also 0 or 1. There are only four possible functions of this type. For each function, we can look at its two output, f, uh, f of 0 and f of 1. And the unknown function is has two choice, whether the function is constant or balanced. But it is profound because it is the first problem where a quantum algorithm, Ditter's algorithm, can answer this question with fewer queries than any classical algorithm. This makes it a perfect test case to show quantum advantage in very clean way. Constant function and balanced function. Data's problem poses a similarly simple question. It is a given function constant or balanced, a crucial first step in demonstrating a quantum advantage. Now let's see the classical approach. How would a traditional computer solve it? A classical approach. Remember, we have black box function f that takes one bit as input and return one bit as output. Our task is decide to if this function is constant or balanced. A classical computer has only one way to sure. First is call the function with 0 and note the output f of 0. This it called the function with inputs 1 and note the output function 1 or f of 1. Now it compares these two results. If f of 0 and f of 1 are the same, the function is constant. If f of 0 and f of 1 are different, the function is balanced. The important point is the classical computer must make two separate queries to the function, one for each input. With only one query, it can never be certain before it only knows one of the value. So For Dieter's problem, the classical approach needs exactly two evaluation of f. This is the best it can do. The classical approach has classical determining if a function is constant or balanced require evaluating it multiple times. The method can be inefficient if answer same answer is equal to say a constant function in different is equal to balance function. Step 1 evaluate. Step 2 evaluate f of 1. Step 1 evaluate f of 0. Step 3 compare result. Then then now now we enter the main part, detach algorithm relaying quantum parallelism. So, which show how a quantum computer can use quantum parallelism. So far, we saw that a classical computer must call the function twice, once with input 0 and once with input 1. The key idea of Ditter's algorithm is to use a qubit in superposition so that the function is in a sense evaluate on both input at the same time. We prepare two qubits and apply hammered gates to create superposition. Because of this, the first qubit now represent both input 0 and 1 together. When we send this qubit through the quantum version of the function called the oracle, the function acts on both input in one go. This is called quantum parallelism. One operation, but information about both f of 0 and f of 1 is proceed simultaneously. Then with another hammered and interference, the algorithm combines this information into a single qubit so that one final measurement tells us whether the function is constant or balanced using only one query. So detach algorithm is only our first clear example of how quantum parallelism can give a real advantage over classical computation, classical limitation and quantum efficiency. First, classical limitation require two queries to the function. Second, limited by sequential processing. Third, one qubit. For either quantum efficiency, solve with a single query. Second, utilize superposition for parallel computation. Third, both qubits 0 and 1 at the same time. Then we are enter the visualizing the quantum circuit, gates and qubit. The algorithm is implemented using a quantum circuit, a sequence of the quantum gate acting on the qubit to achieve the desired outcome. What each part does. X gate purpose sets bottom qubit to first H superposition. So oof encode function as phases. Second H interfaces measure read 0 is equal to constant, 1 is equal to balance. Then we entered. Now I want to explain the real message of detach algorithm. The power of one query. Why detach algorithm matters. Why this small problem actually matters in detach problem. A classical computer must query the function twice. It needs f of 0 and f of 1 to decide if the function is constant or balanced. There is no classical trick that can avoid these two queries. Detached quantum algorithm does something different by putting the input qubit into superposition and using interference with an oracle. The algorithm efficiently processes f of 0 and f of 1 together in just one quantum query. After a final hammered and a measurement, a single qubit of result tells us constant or balance. With the uncertainty, it is the first clear example that quantum computer can outperform all the classical algorithm for a specific task. In terms of query complexity, the idea later grew into more powerful algorithm like detach, sure and goer, but it all start from the simple one query success. Then in this there are many sure quantum many things. The big win one versus two query, First, in this classical computer, always need to query quantum computer just one query get both answers. Simple but proves quantum is faster. First, prove quantum beats classical. 1985, data show quantum advantage edges. Small win, 1 versus 2, but proves the principle. Show quantum computing is not equal to classical computing. Open door to bigger speed up. Now let's talk the implementation of detached algorithm, detached and future paving the way for sure and grower. Then, like detached algorithm was the first algorithm to show the real quantum advantage. It solved a problem with one query. That classical need to the speed up is small, but the idea is big. It proved that by combining superposition and interference, we can design algorithm that use information in a complete new way. Not possible for a classical computer. Sure, algorithm which factor large number efficiently and theoretic. Classical cryptography. Grover algorithm which speed up unstructured search problem. So detached algorithm is like a small prototype that open the door to an entire family of powerful quantum algorithm and show research how to think the quantum way when designing a new algorithm for the future. Detached algorithm laid the groundwork for more complex quantum algorithm like Shor and Grover. 1985, detached algorithm first quantum advantage 1 versus 2 query. 1994, Shor algorithm break encryption factoring huge number. 1996, Grover algorithm database search. This algorithm promised to evaluate field for cryptography to material science. Key principle carried forward. Superposition, check all input at once. Interference, cancel wrong answer. Phase kickback, encode information in phases. Oracle queries, backwards efficiency all used in Shower plus Grower. Then, now I conclude my presentation with the conclusion, the dawn of the quantum computing. In this talk, we started with the limits of classical computation, with where bits are only 0 and 1. Uh, and problem must be checked step by step. Then we introduce quantum ideas like qubit, superposition, and interference, which let us process many possibility. And the same time, using this idea, we solve detailed problem, deciding whether a simple black box function is constant or balanced. Classically, this needs two query. Ditter's algorithm showed that a quantum computer can solve it with just one query. The speedup is small, but the message is very powerful. Quantum mechanics can be used to build computers that outperform classical ones for certain tasks. The data prove that beats classical 1 versus 2. 1 versus 2 queries. Superposition check all the inputs at once and many more. Real future impact. Crypto. Sure breaks RSA. Bank preparing now. Drugs. Implant molecules. New medicine faster. AI. Grower speeds machine learning. Material. Design perfect batteries. Superconductor. That's why today quantum industry now 30 billion industry. Detached algorithm is cornerstone, proving that quantum computer can perform tasks impossible for classical machine, making the true dawn of a new commercial area. The universe is not classical, it's quantum, and so is information state better. Thank you. Now, I would like to conclude my presentation. Today, I start showing the limit of classical communication computation where bits are only 0 or 1 and problem must be checked step by step. This introduced the key quantum ideas like qubit, superposition, ideas like qubit, and interference. Using these tools, we look at Ditter's problem and so saw how a classical computer needs two queries to decide whether a function is constant or balanced and more. So detached algorithm is and more. So detached algorithm is also called quantum leap because it marks the beginning of the thinking about communication competition in a truly quantum way. Thank you.